Welcome. In this lecture, which has multiple sessions, we'll explore methods for finding a minimizer of a function that has a scalar argument. We'll explore iterative methods specifically. So the main concepts for this are, we'll derive what we mean by a step size and a search direction, and we'll understand why fixed step sizes require user knowledge. We'll examine how some simple methods can perform poorly. They can perform well, but we want to see how we can improve them. And one of the ways that we'll look at is an algorithm using an exponential method that will help the user to find a better step size. And we'll end this lecture with our Miho backtracking, which is a combination of step size selection and how to perform a comparison. Through this, let's remember our dynamical system. We'll keep using that through this lecture. And the problem that we want to solve is how to automatically select a step size with as little information as we can manage. How about if you and I explore what we mean by iterating an estimator? What we might mean is that if we are given a current value of the minimizer, so we'll be thinking ahead that this will be starting T1, T2, T3, etc. And let's suppose that we're at step K and that we're given a function with a scalar argument, and I'll just say, and we're given enough other information that we can solve the problem. What we want to do is estimate a new value of the minimizer, which we'll call K plus 1. To do this, let's consider a truncated Taylor series. So we will consider, we'll approximate using a Taylor series. We'll say that the function at any scalar argument is approximately the function expanded around our current estimate plus the first derivative at the current estimate times the difference between the scalar argument and the expansion point. And then there will be a second order term, which is the second derivative at the expansion point over 2 times the difference between the scalar argument and the expansion point squared. What we would like to do, if we look at this carefully, we can see that this is a quadratic approximation. And a quadratic approximation has a single global minimizer. So what we want to do is we seek tk plus 1. Now, what condition might we want to put on tk plus 1? Well, what I'd want to do is I want to see tk plus 1 be a minimizer of this. So see tk plus 1 that is stationary. That is, what we want is we want f evaluated at tk plus 1. Well, we don't know what that is, but we sure want the derivative at tk plus 1 to equal 0. How could we go about doing that? Well, we could differentiate this function, and then we could substitute in and see where we are. Let's try that. So let's differentiate. And when we differentiate, what we see is we differentiate the left-hand side, and then we'll keep this approximation for now. And now we differentiate the right-hand side with respect to t. Well, that is 0. And then that, with respect to t, is just f prime. Okay, so that's f prime at tk. And then when we differentiate this with respect to t, not to tk, but with respect to t, oh, now we have to use the chain rule. So the 2 comes down, and then the 2 divided by 2 cancel out, and then we multiply through, and then, so what we see is that that is plus f double prime evaluated at our current point times t minus tk. So now what we'll do is substitute and equate to 0. That is, so the substitute is we're going to insert our tk plus 1, and then the equate to 0 is what we want to do is we want tk plus 1 to be stationary. So that is saying that we want f at tk plus 1, which f prime equals, so that is f prime at tk plus f double prime at tk times tk plus 1 minus tk, and we want to set that equal to 0. So when we do this, so now what we'll do is we'll solve for tk plus 1. That is, we want tk plus 1 to be on the left-hand side of an equation. So I would like you to work this out. I'd like you to write this down and then to solve for that tk plus 1 using ordinary algebra. And when you do, the answer that you should get is tk plus 1 equals tk minus the first derivative of the function evaluated at our current point divided by the second derivative of the function evaluated at our current point. That's what you should get. Now, we will start writing this in a particular way. So we will say that we will define the direction and this is at step k, or actually not step, let's say iteration, because step, we'll want to use that word multiple times. So define the direction at iteration tk, and we'll use the symbol d sub k to be, we'll say that d sub k is equal by definition to minus f prime at tk. And we will define the step size to be the ideal step size under all of these assumptions will be defined as 1 over the second derivative of the function evaluated at our current point. So this is the algebra. Let's pause for a moment and think about the geometry. Let's suppose we have a function, and that function is locally convex, and that this is our current estimate, and we take the derivative. So if we take the derivative of this function, it's pointing downward, so it's a negative number. And when we say that the direction we're searching is the negative of the derivative, that means that for a downward pointing slope, we're searching in the positive direction. And likewise, if the function looks like this, and this is our current estimate, then that's positive. And if derivative of the function is positive, that implies that we want to search to the left of it, so we want to search in a negative direction. So that is what's going on here. Now, this step size, the rest of this lecture, all the subsequent sessions, will be based around this idea. Suppose that the user doesn't know the second derivative of the function. That is, suppose they just, this may be too complicated, it may be computationally unavailable. So suppose that the user can't supply us with that second derivative. What the user will then have to do is they'll have to supply us with this step size for us to be able to get the iteration. So let's, now that we've got this geometry and this understanding, our iteration is, we will say that at k plus 1, we will set that to be the kth estimate plus the step size for iteration k times the direction for iteration k. So that's the iteration that we'll be looking at in the subsequent sessions.